Welcome to This Explainer. Okay, today we're diving into a pretty fascinating challenge in modern medicine. You know, when doctors evaluate a patient, they rarely rely on just one single test, right? I mean, they might look at an MRI to get those really crisp anatomical details, and then maybe a PET scan to check on metabolic activity. But how in the world do we get artificial intelligence to synthesize multiple completely different types of medical data like that? Well, researchers have been building some incredible deep learning models to do exactly this, and today, we're going to break down exactly how they work using a brand new framework.
So let's just get right into it. When we talk about analyzing separate medical images, again, like an MRI and a PET scan, the fundamental problem isn't actually getting the data into the computer. The core problem is figuring out where exactly in the neural network these different streams of information should merge together. Do we mix them all up right away? Do we wait until the very end? This one simple question, where does fusion happen, literally changes everything about how an AI learns.
A taxonomy proposed in a 2024 paper by Lee and colleagues brilliantly lays out the solution. They categorized multimodal fusion into three main stages: input, intermediate, and output. And honestly, the analogies here make this so easy to grasp. Think about it like cooking. Input fusion? That's like mixing all your raw ingredients together in a big bowl before you even start cooking. Intermediate fusion is more like two expert chefs preparing separate dishes in the same kitchen, but kind of sharing their ideas before plating the final meal. And output fusion? That's like each expert tasting their own finished dish completely independently and then just voting on a final score. So we're basically looking at fusing data before, during, or after learning.
Here is our roadmap for today. 1. Input fusion, early integration. 2. Intermediate fusion, feature level. 3. Intermediate fusion, subtypes. 4. Output fusion, final decisions. And 5. The big picture summary.
Section 1. Input fusion, early integration.
Starting at the very beginning of the deep learning pipeline, the core philosophy here is super simple. Fuse first, then learn. Going back to our cooking analogy, you are literally throwing all your ingredients into the same bowl before you even turn on the oven. The network hasn't learned a single thing yet. You are just physically combining that raw data right off the bat.
Notice how the raw images on the left side, the MRI and the PET scan, are pushed into a merge module before they ever even touch a neural network. The modalities are literally concatenated or stacked together right at the pixel or voxel level. It's only after they're mashed up into one multi-channel image that the data flows into that single yellow box on the right, the CNN backbone. So the neural network is learning from combined data right from the very start.
Now, this approach definitely has some distinct pros and cons. The absolute biggest advantage is that it's a really simple architecture. You only need one backbone network, which means a lower parameter count, and it learns those joint representations early on. But here's the catch. It absolutely requires perfectly aligned or registered modalities. If a patient even just coughed and moved a tiny bit between their MRI and their PET scan, this method kind of falls apart. It's super sensitive to resolution differences and noise, and it really struggles if one of the modalities happens to be missing.
Section 2. Intermediate fusion, feature level.
Moving a bit deeper into the network, we find what is easily the most nuanced category of the whole taxonomy. If input fusion was fuse first, then learn, the definition here is the exact opposite. Learn separately, then combine features. So instead of combining raw pixels right away, we let the network learn the unique characteristics of each image type first. This captures much richer semantic information before it ever tries to mix them together. Take a look at how that orange fusion module has physically shifted to the right. It's sitting right there between the separate green feature extractors on the left and the final purple classifier on the right. So each modality gets its very own CNN to extract features. Once those specific, high-level features are pulled out into those blue and green blocks, then they're fused together and sent over to the classifier. Because it captures all that complementary info, this generally achieves much higher predictive performance.
Section 3. Intermediate fusion subtypes.
Now, because prediction accuracy almost always trumps simplicity when we're talking about life-saving medical AI, researchers actually divided this intermediate stage into three distinct architectural subtypes. The first one is single-level fusion, which just follows three straightforward steps. Step 1, extract features separately for each modality. Step 2, fuse those features exactly once. And Step 3, send that single fused representation to the final classifier. Fun fact, this is actually the most widely used strategy in multimodal deep learning research right now. Under the hood, it looks like this. Separate feature extractors on the left generate those blue and green feature maps. Then,
Bam! They hit that yellow fusion box once. It's incredibly efficient and super easy to implement. It's exactly like two experts working in their own private offices and then coming together to share their ideas exactly one time before making a final decision. The limitation, of course, is that since they only fuse once, the network only gets one single opportunity to exchange information. That means it might entirely miss out on deeper, multi-scale relationships.
And that limitation brings us perfectly to the second intermediate subtype, hierarchical fusion. The guiding principle here is to fuse many times across the network. So instead of just one quick meeting between our experts, this strategy is purposely designed to capture relationships at multiple different scales.
Just look at the sheer complexity here compared to what we just saw. Notice those red lines and yellow fusion boxes repeating vertically across the diagram. The network is fusing low-level features at level 1, mid-level features at level 2, and high-level features at level 3. It's like our medical experts discussing their findings after every single— actually, it's more like they're checking in with each other after every tiny step of their analysis. This brilliantly captures both local and global info for a much better multi-scale representation. But as you can probably guess, this is a way more complicated architecture. Surprisingly, some of these hierarchical models can require hundreds of millions of parameters. You're going to need massive computing power and huge datasets to pull this off.
Okay, the third and final intermediate subtype is attention-based fusion. The mantra here is, learn what to pay attention to before fusing. If you've been following AI, you know this is incredibly common in modern transformer architectures, and it is widely known for delivering absolutely stellar performance.
Let's quickly break down this attention mechanism. Look at the yellow attention module right there in the center. Notice those numbers? 0.40, 0.35, 0.25. The network is literally calculating dynamic weights on the fly. It's deciding, for this specific patient, which modality is the most informative. Maybe for patient A, the MRI is way more useful, so it gives those MRI features a higher weight. But for patient B, maybe their PET scan is the critical piece of the puzzle. It learns these weights dynamically. It's incredibly adaptable, for sure. But the trade-off is that it's computationally expensive, definitely harder to interpret, and it requires a ton of training data to learn those complex weight distributions accurately.
Section 4. Output Fusion. Final Decisions.
Arriving at the very last stage of our spatial journey, the definition shifts one last time to predict separately, then combine decisions. In this setup, independent models do all of the heavy lifting completely on their own, from start to finish.
Notice how that yellow fusion block is now pushed all the way over to the right end of the flowchart. We have completely separate CNN models for modality 1 and modality 2, and they don't just extract features, they go all the way to generating an independent prediction. It's like, maybe there's an 80% chance of a tumor according to the MRI model and a 70% chance according to the PET model. Only then do those final predictions hit the fusion block. It acts exactly like independent experts who literally never speak to each other, each making a separate final decision, and then they just tally up a vote.
So what you should really take away from this is that output fusion is incredibly easy to deploy, especially if you already have existing pre-trained unimodal models just lying around. It's also great if your modalities are wildly different, like highly heterogeneous. But there's a massive limitation. It completely misses out on learning complex interactions between the different data types. Because the networks literally never communicate while they're extracting features, they can't learn how a specific pattern in the MRI might relate to a specific pattern in the PET scan. The final performance depends entirely on the quality of those individual isolated models.
Section 5. The Big Picture Summary. We have covered a lot of ground today, but viewing these side by side really provides a great aha moment. Just look at the yellow fusion boxes across the three main architectures. In input fusion, the box is on the far left. It's simple, requires one network, but demands perfect physical alignment. In output fusion, the box is all the way on the far right. It's totally independent, relies on a final vote, but it misses out on those deep cross connections. And right there in the middle, we have intermediate fusion. The box sits right in the sweet spot between feature extraction and classification, giving researchers the flexibility to use single-level, hierarchical, or attention-based strategies. The literal location of that fusion block completely defines the model's capabilities, its computational cost, and its overall complexity.
So I want to leave you with a final thought to ponder. We've seen that input and output fusions are definitely simpler and cheaper, while intermediate fusions, especially the attention-based ones, are highly complex but often way more accurate. If you were the one designing a system to make a life-saving medical diagnosis, which strategy would you choose? How do you weigh those trade-offs of simplicity, computational cost, and interpretability against raw, complex accuracy when human lives are actually on the line?
It's a heavy question, and it's one AI researchers grapple with every single day. Thanks for joining me on this explainer, and keep questioning how the models of tomorrow are being built today.